We now go back to pants and shirts in exactly the same scenario that we already graphed in graph 7.7, except now we'll add some numbers to it. We'll again assume that my utility function is Cobb-Douglas, this time with exponents of 0.5 and 0.5. In other words, we place equal weight on the shirts as well as the pants. We'll also assume that I come to the store with $200, that the price of pants is $20, and the price of shirts is $10. We thus start with our now familiar blue budget constraint that has a vertical intercept of 20 and a horizontal intercept of 10. And we know that the optimal bundle A will occur at a point of tangency with an indifference curve. The indifference curve here is derived from our Cobb-Douglas utility function. We solve for this optimal bundle A with the tools developed in Chapter 6. We just maximize utility subject to the fixed blue budget constraint, set up the Lagrangian, get first order conditions, and solve those for x1 and x2. When we do that, we get that my optimal bundle A has me consuming 5 pants and 10 shirts under the present economic circumstances. We then imagine that my economic circumstances change through the introduction of a coupon that gives me 50% off on pants and therefore reduces the price of pants to $10. This is illustrated with the new magenta budget constraint, and we indicate my optimal bundle C on that magenta budget constraint with another point of tangency. Again, the indifference curve drawn here is directly derived from the utility function that we're using in this problem. Mathematically, we solve for bundle C in exactly the same way we solved for bundle A. That is, we maximize utility subject to a fixed budget constraint, except now we use the magenta budget constraint where the price of pants is $10 rather than $20. When we go through the usual steps, we then calculate that I will now consume 10 pants and 10 shirts. I will therefore increase my pants consumption, but leave my shirt consumption unchanged as a result of the coupon. To solve for the pure substitution effect in this case, however, we have to set up an expenditure minimization problem. We take the final prices, in other words the final slope of the budget constraint, and ask how much can we shift that budget constraint in and still reach the original indifference curve that's labeled as UA. Graphically, this simply involves drawing the compensated budget constraint, which is the budget constraint that has the slope of the final budget but is tangent to the original indifference curve. For the utility function that we are using, the point of tangency B occurs roughly at 7 shirts and 7 pants. Again, we calculate this by setting up the expenditure minimization problem that says what's the minimum expenditure necessary given that we'd like to reach the indifference curve UA when the price of shirts and pants is both equal to 10. So, we started with the utility function x1 to the half times x2 to the half. We set up the utility maximization problem as maximizing this utility subject to the budget constraint. Since we're going to end up changing the price of pants, P1, we'll just leave that in the budget constraint as P1 and express the budget constraint as P1x1 plus 10 times x2 equal to 200, where we put in the price of x2, the price of shirts, as 10. When we solve this problem, we get that x1 is equal to 100 divided by P1 and x2 is equal to 10. So our shirt consumption remains at 10 regardless of what the price of pants is. But our pants consumption changes with the price of pants. If pants cost $20 as they do without the coupon, then my consumption is 100 divided by 20, or just 5. If the price of pants goes down to 10 as it does with the coupon, we get consumption of 100 divided by 10, or 10 pants. We can then find the label on the indifference curve UA by plugging in 5 pants and 10 shirts into the utility function x1 to the 1/2 times x2 to the 1/2. This gives us the value that we need in order to set up the expenditure minimization problem, which says we'd like to minimize our expenditure at the after coupon prices so when our budget is 10x1 plus 10x2, subject to our utility being equal to that label on the indifference curve that passes through bundle A. We now combine panels A and B in panel C. In panel A, we figured out the change in the consumer's behavior when the price changes, the move from A to C. In panel B, we isolated the portion of that change in behavior that's due to the pure substitution effect, the move from A to B. When we put the two panels together in panel C, we can now say that the pure substitution effect is the move from A to B, and the pure income effect is the move from B to C, because when we move from B to C, we're jumping between parallel budgets where the only difference is a difference in income. Notice that bundles B and C lie on the same ray from the origin. This is no accident. Cobb-Douglas tastes are homothetic, and homothetic tastes have the property that indifference curves have the same slopes along the same rays from the origin. So if we look for tangencies along budget constraints that have the same slope, those tangencies must lie on the same ray from the origin if tastes are homothetic. To conclude, note again that whenever we're trying to figure out what a consumer actually does, we're using the utility maximization problem, because we're asking what's the best the consumer can do given the economic circumstances she faces. That's how we arrived at bundle A and bundle C. But when we're trying to isolate a substitution effect, we're asking a hypothetical question. We're asking the question, what's the minimum spending necessary to get a consumer to a particular indifference curve? So then we have to use the expenditure minimization problem. In our Cobb-Douglas case, we get a positive substitution effect on the pants axis when the price of pants decreases, as we should. Substitution effects always say consume more of the good that's become relatively cheaper. We also get a positive income effect on the pants axis because pants are normal goods when they're modeled through Cobb-Douglas preferences. On the vertical axis, we get a negative substitution effect as the price of pants decreases, which again is as it should be. Substitution effects always say consume less of the good that's become relatively more expensive, and when the price of pants decreases, shirts have become relatively more expensive. But that negative substitution effect is then exactly offset by a positive income effect on the vertical axis, because shirts are still normal goods when tastes are Cobb-Douglas. Note, however, that exact offsetting of income and substitution effects on the vertical axis simply arises because we used Cobb-Douglas tastes that assume an elasticity of substitution equal to 1. Were we to use tastes that have a smaller elasticity of substitution, the substitution effect would be smaller, and as a result, the income effect would more than offset the substitution effect and our shirts consumption would increase. If, on the other hand, we used a larger elasticity of substitution, we would get a larger substitution effect, and the income effect would not fully offset the substitution effect, causing our shirts consumption to decline as the price of pants decreases.